We will see if this works. All right, so this is now the first real class of the semester. In order to try to make this doable and viewable for those of you who are watching at home, Kayla has kindly provided 2 pictures to brighten up the classroom and to try to keep me from going too far to an extreme. We'll see later if this is actually visible on the camera over here. But OK, so what I want to do today is talk a little bit about various issues in analysis. I trust you can all read Chapter 11 on Fourier analysis and master the definitions. So I don't want to spend time in class doing that. Instead, I want to try to spend time in class going over some of the technical issues that really plague any serious course in analysis and any serious applications of analysis. So one of the biggest differences between mathematicians and physicists is the rigor of the steps done. Professional physicists, by a winnowing process, have learned which steps can be done, and they actually do things that can be justified. They just don't do the justification. Okay, if you go even further to philosophy, well, I won't go that far. All right, what I want to do today is I want to talk about how you would try to justify some of the dealings with infinities that we have in analysis. This is one of the hardest issues in the subject. And the real difficulty is, if things are finite, not a big deal. You don't have to worry too much. If things are infinite, then all of a sudden order matters. Depending on how you do things, you can get different things. How many of you know the rearrangement theorem? OK, so the rearrangement theorem. So what it says is, say you have a series AN that converges conditionally, not absolutely. Then you can rearrange so that lim_inf of AN equals A and lim_sup of AN equals B for any A and B. And what's the one restriction I need on A and B? So I can rearrange it so that the lim_inf is A, the lim_sup is B. What restriction do I need on A and B? A is less than B. Can do a little bit better than A is less than B. Less than or equal to B. So we can put in the annoying equal sign, OK? So the way this works is the following. If the series converges conditionally but not absolutely, if I put in absolute values, it goes off to infinity. So look at the sum of the positive values and the sum of the negative values. The sum of the positive values goes to infinity. The sum of the negative values goes to negative infinity. So what you do is you take your series and you keep adding terms until you first get above B. And you've written going through the positive terms in order. Then you start adding the negative terms until you first dip below A. Then you add positive terms until you get above B again, the negative terms until you get below A, and you keep doing this. Because the series converges conditionally, the size of the terms has to be going to 0. So the overshoots of A and B have to be getting smaller and smaller and smaller with some kind of estimate. So with work, you can make your lim_sup and lim_inf whatever you want other than just this trivial restriction. So this tells you you've got to be very careful. If I have a sum that only converges conditionally, I can't just rearrange at whim. All right, so what I want to do now is I want to start talking about Taylor series. So hopefully everyone is familiar with Taylor series. And so given some function f, we map it to a new function, say Tn of f. And we let Tn of f at x be a sum, n goes from 0. Oh, let's do, I'll do n. We'll do m goes from 0 to n of a sub m x to the m. So what we're doing is we're taking a function and we're approximating with it a finite polynomial. So why might it be a good idea to approximate a function with a finite polynomial?
You can actually compute it.
Yeah, you could actually compute it. That's actually useful for things. It's much simpler to deal with a finite polynomial. I can differentiate it easily. I can evaluate it easily. Lots of great things I can do. There's a couple of questions you can ask. And so one of the big things I want you to get out of this class is when you see mathematics, what questions should you ask? How should you look at things? So what's some questions we could ask about this? So give me some questions. Yes?
Under what conditions does that converge?
OK. And you can actually even be a little bit more specific than when does it converge. Be a little bit more specific. Under what conditions does it converge?
Absolutely conditional.
Okay, so there could be types of convergence. What else could we have?
When does it converge to F?
When does it converge to F? And I'll also throw down in rate of convergence. How quickly does it converge? So these are all great questions you could ask. What other questions could I ask about this? Question?
I was wondering, it has to be real analytic to converge to F, right?
By definition, if F is real analytic, it is given by its series expansion, yes. But then, of course, this begs the question, what is real analytic? And so if you ever take a physics class, thermodynamics, they will tell you, what is the definition of an ideal gas? An ideal gas is that which obeys the ideal gas law. And the ideal gas law is the law which describes the behavior of an ideal gas. Yes. All right. What other questions can we ask about this? This is preparing you for grad school. The way this is preparing you for grad school is when you go to a talk, it is a rule that every talk must have at least one question. You want the speaker to feel like somebody gave a damn. Even if they don't, you want them to feel like somebody actually paid attention. Okay? And there's a whole slew of standard questions you can ask. And frequently these lead to things that the speaker forgot to investigate, or good generalizations. And I have done numerous papers with colleagues. Some of the small projects this summer came from asking these questions at a talk. So if you can just learn a set of standard questions to ask, this will serve you well. What else could we ask?
For which x is it valid?
Okay. For what x? So i.e., where does it converge? So maybe it doesn't converge everywhere. I think it's similar to when, but what else could we ask? So there's two big questions you've missed. And these should become automatic questions. So another one, we'll call this one prime. 2. What are the x's? I'm sorry, not the x's, the AMs. I'm giving you the series expansion, right? What are the AMs? How do you find them? Is it hard or is it easy to find them? If you do something in complex analysis, we actually have nice integral formulas to find these AMs. But in real analysis, we have to do maybe some differentiation or... So there's one more natural question to ask. That would be very similar to the rate of convergence. Any Life of Brian fans? No. Uniqueness. So when we're talking about, does it converge to F, could we have multiple Taylor series converging to the same things? Could two distinct Taylor series converge to F? Right? And that's going to be a fascinating question. Do you think the Taylor series should be unique? I give you a function, it should have a unique Taylor series. So from what you've seen in Taylor series, this is a natural thing to wish for. So, example, let's let g of x be e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. This is one of my favorite or least favorite functions in real analysis, depending on how you want to look at things. How many of you have seen this function before? Okay. The name of this function is why real analysis is significantly harder than complex analysis. It's a little long to write that on the board, so I abbreviate it as G. Okay? What do you think a plot of G looks like? Or better yet, where do you think G is interesting?
0.
At 0. away from 0, everything is nice. But at 0, I have a split in my definition. So what do you think this function looks like near 0? You want to get a rough sense. You want to look at it. How does it look? OK. So for those of you who are not able to see the class, it's something like this. I feel like some kind of charade game here. This function has extreme decay near the origin. Let's let x be 1 over n. Then I put this and I get e to the negative n squared. So if x is 1 over 10, this is e to the negative 100. If x is 1 over 1,000, this is e to the negative 1,000 squared. OK, this function, e to the negative 1 million, that's damn small. This function is extremely rapidly decaying near the origin. In fact, it's so rapidly decaying that the mth derivative of g at 0 is equal to 0 for all m. The way you see this is how? Can I just take the derivative of each piece and match? No. I have a split in definition. What do I have to do to find the derivative?
Left and right hand. Left and right side.
OK, so I have to go back to the definition of the derivative. G of 0 plus h minus g of 0 over h. Fortunately, it doesn't matter if h is positive or negative. The limits are both going to be the same. And when you do that, unfortunately, you're going to have 0 over 0. You'll use L'Hopital's rule. So I haven't decided yet if I'm going to assign this as a homework problem or just going to encourage you to do this. Do you want me to decide right now? Yes or no? OK. No preference as to whether or not I decide now? I will just let you know at some point. All right. It's definitely a calculation you should do. And when you do this, you actually get the Taylor series. And we'll do the infinite one, is identically 0. Let's think about what this means. It means the only place where this agrees with my original function is at the origin. And again, I'm assuming right now that you actually know what the Taylor series is, and that you know the Taylor series of a function g at x is the sum of the mth derivative at 0, x to the m over m factorial. M goes from 0 to infinity. I'm assuming you know this. And so what this tells us is the Taylor series, the infinite Taylor series approximation, agrees with my function only at the origin. Well, if you look at how the Taylor series is defined, it's defined as g of 0 plus a multiple of x. So when you take x equals 0, you are forced to agree at the origin. This is the least impressive result possible because by definition you are forced to agree there. What it is telling you is it agrees no place else. This is the worst possible you could have. The region where it converges is essentially just one point. And that's the point that you have to get no matter what. So this tells you why real analysis is so hard. I have a nice infinitely differentiable function, but it doesn't even equal its Taylor series in a small neighborhood about the origin. It only equals its Taylor series at a point. Is all hope lost? Well, let's look at some of the other questions we have. One question is we can ask rate of convergence. Well, this does not equal the function we want. It's damn close, right? And so even though it does not equal our function, it's so close to our function that for many practical purposes, it's fine. But subtleties like this make real analysis significantly harder than complex analysis. I know this is being recorded. I view complex analysis as sort of like the country club of mathematics. The country club before all the lawsuits have come in, forcing them to open their membership to all qualified people. This is a very exclusive subject to complex analysis, and they do not let in most functions. So the only functions that are let in into complex analysis are really nice. And so they have a lot of wonderful properties. In complex analysis, if you're differentiable once, you are differentiable infinitely often, and you equal your Taylor series in a neighborhood. So that's an absolutely wonderful property. All right, so what this is telling us is we have to be careful when we start to work with infinite sums. There's a lot of very natural questions to ask, and unfortunately, sometimes the answers will not be what we want. There's other questions we could ask about Taylor series. And just in the interest of time, one question you could ask is, what if you have two variables? What would be a two-variable Taylor series look like? And then, of course, once you get to this, the next question you should ask is to try to remove the blinders. We're expanding in the basis 1x, x squared, x cubed, x to the fourth, etc., etc., etc. I am a Bostonian. I am proud of being a Bostonian. I, for the most part, do not like New York City, especially certain sports teams. But I have to admit that there is one thing New York City does better than Boston. And if you say the wrong thing, your grade will suffer. As a Bostonian, what do I have to give New York City credit for? Or at least a subset of New York City. One of the, yes? The layout. In Manhattan, Manhattan is a beautiful grid system. Boston, you have roads like this where they cross, this is, who knows Boston geography? Comm Ave and? Okay. There are streets in Boston where they flip as to which one is above the other. I mean, the geography in Boston is absolutely atrocious. The whole point of linear algebra is how to choose the right basis for the problem you're looking at. And so 1x, x squared, x cubed, this is a very convenient basis in terms of differentiation, but it may not be the most convenient basis for expanding the function and transmitting information. One of the whole ideas of Taylor series is by setting just a few coefficients, you can get a great sense of what the function is looking like. Instead of using this basis, we're going to use another basis. What basis are we going to use? So what basis do you think we're going to be using?
E sub n of x.
Yeah, E sub n of x. This is why this is the chapter on Fourier analysis. We're going to switch to the Fourier basis. There's other bases, there's wavelet bases. It's all about finding vectors that have really nice properties. And the problem with these vectors here, the 1x, x squared, x cubed, is in some sense they're not orthogonal. They're not mutually perpendicular. It's much better to express something as a sum of perpendicular directions. And that's one of the reasons why we like some of these other bases. And the idea is when you're transmitting information, like streaming video, such as some of you at home watching now, what you want to do is you want to use the fact that you have powerful computers on both ends. And you don't want to transmit every single pixel. You want to transmit maybe the difference between two images, so only small things have to be updated. You can break up a screen into, what is it? Is it red, green, and what's the other color? Is it blue? Blue. You can do two-dimensional plots of like the red, green, blue pixelization. Yes?
Is it possible that there's like a different inner product where those are orthogonal?
There is. If you introduce different weights, you can I don't know if you can make these ones orthogonal. You might be able to by choosing an appropriate weight function. I'm not sure. And then that is one way to try to fix these things. So if you look at Hermite polynomials, they have a weighting factor, which is, I believe, like an exponential with a negative x squared. And something like that will fix some of the issues. And then it just becomes computationally which is best. But if I want to do streaming video, if I send red, green, blue pixel values, I get a great sense. So I have like a two-dimensional function for each one of these. I approximate these using a two-dimensional Taylor series or a two-dimensional Fourier expansion or a two-dimensional wavelet, whatever. And I just transmit a couple of coefficients. And that allows me to reconstruct these very accurately. And once I reconstruct these, I have a really good sense now of what's going on. And I can get my image back without too much difficulty. OK. Any questions on stuff along these lines? So we could also add higher dimensions. And then just trying to figure out what are the issues when we switch to higher dimensions. OK. So what I want to do now is I want to talk a little bit about continuity and uniform continuity, because these are the tools we're going to need to handle things. And then I'm going to apply them to a very special case, the geometric series. And the reason I like the geometric series is the geometric series is very, very tractable for calculations. And it's a great way to see what's going on without getting lost in all the technical details. And then from that, we can generalize to what's going on in, for arbitrary cases. OK, continuity. Do you still remember the definition, the rigorous math definition? OK, so this is for all epsilon greater than 0, there exists a delta such that if y does not equal x and x minus y is less than delta, then f of x minus f of y is less than epsilon. And this is continuity at a point x. If I wanted to, I could drop the condition that y doesn't equal x, because if y equals x, this is pretty trivial to show. I actually don't like the way that this is written. There's something that's being hidden a little bit. So what's being hidden a little bit with the notation here? It's not wrong notation. It's correct. This is what it means to be continuous at x. For every epsilon, there is a delta such that if x minus y is less than delta, then f of x minus f of y is less than epsilon. I want to have a little bit more elaborate notation. And so really, delta is some function of x and epsilon. And for the most part, we don't bother writing this. Why? Because if we kept writing all the subscripts that everything depends upon, our papers and our books would become these nightmarish things, and we, unlike Charles Dickens, are not paid by the word. Okay? He was paid by the word. You can look it up. It explains Tale of Two Cities, Great Expectations. You know, we don't want to write this. But when you don't write this, what's the danger? You forget that delta depends on x. You forget that delta depends on epsilon. The dependence on epsilon is not so bad, but the dependence on x is important and is often forgotten. So the difference between continuity and uniform continuity, delta of x epsilon equals delta of epsilon. That's the main difference between continuity and uniform continuity. You can choose one delta that works for all x simultaneously. And so which is the stronger condition, continuity or uniform continuity? Uniform continuity, right? You've put something else on it. So we have lots of theorems. So for instance, theorem, if continuous on compact set, then uniformly continuous. Is every function that's continuous uniformly continuous? No. So the standard example is f of x equals 1 over x on, say, the interval 0, 1. And so if you look at it, it's going to look something like this. And so here is a function where, as I get closer and closer and closer to 0, the function is getting larger and larger and larger. All right. So over here, as I go far away from the origin, there's no problem. There's no difficulty at all in what's happening. The difficulty is what's happening near the origin. Now, if you choose any specific value of x, I just have to choose delta so that I don't hit the origin. And you give me an epsilon, and I can figure out exactly what delta I need to take. So it's a nice exercise, figure out what delta should be in this case. So it's continuous at every point, but it's not uniformly continuous. All right, so the issue here was at a boundary point. Could you ever have a function that is continuous at an interior point, but not uniformly continuous there? So could I have a function that's continuous at a point, but not uniformly continuous at that point, and that point's an interior point? So if this is my set, I'm in something over here, I have all of these points in my set, and here's my point maybe in the middle. Is it possible to be continuous there, but not uniformly continuous? Good, why not?
Because you could just make a compact set around that.
Excellent. We can just make a compact set around that. And so if you're uniformly continuous on an interior point, if you're continuous on an interior point, you're going to be uniformly continuous there. The difficulty is going to be what happens at the extremes. All right. So what we want to do now is we want to talk about sums of series. And so radius of convergence. How many of you are comfortable with radius of convergence? Okay. So this is one of the issues where, at Williams, we split up the Calc 3 students, for those of you who actually take Calc 3 at Williams. And we say, if you remember sequences in series, then we put you into 151, and we don't really do sequences in series. And now this is where it comes back and bites you. And if you've done 150, most of the time you don't continue this deep in mathematics. Not always, but. So it's a dangerous situation to be in right now. So let me just briefly review sequences and series right now. So we have a sum, say the sum of an x to the n. Question is, when does it converge? And so there's lots of different sequences and stuff we can use. One of my favorites, and in fact a lot of the theories built up from this, is the geometric series. So the sum of r to the n, and it goes from 0 to infinity, converges if the absolute value of r is less than 1, else it diverges. There's lots of different ways to prove this. So one way is to say, let's let Sn, or maybe do a capital N. Sn is 1 plus r to the n. This is the boring proof. R times Sn is r plus r to the n plus r to the n plus 1. If we subtract, what do we get when we subtract? We get 1 minus r times Sn is 1 minus r to the n plus 1. And so when we do it like this, we can then solve and say Sn is 1 minus r to the n plus 1 over 1 minus r is 1 over 1 minus r to the n plus 1 over 1 minus r. So this is the standard algebra proof that the geometric series converges. If the absolute value of r is less than 1, then as n goes to infinity, this second term here becomes negligible. So not only do we get convergence, we actually get rate of convergence. Okay? It turns out this is the most important series for trying to understand convergence. And a lot of our tests on convergence are based on an understanding of this. So if I didn't have to bring the tripod down, and if this was a lower level math course, I would have brought my basketball net. And so how many of you have seen my lecture? At least 2 of you, 3 of you, I think have seen, you can prove the geometric series by playing a game of hoops. Okay? I'm going to just quickly go through that because it shows you good proof techniques. So here, anybody know what this is called in terms of how we do this argument? The key phrase? Telescoping. Excellent. So this was the telescoping sum. And what it's saying is if you look at it the right way, the calculation isn't so bad. All that survives is the first and the last. This is a great tool in a lot of analysis problems. And all this stuff in the middle cancels out. This is why it was so clever to multiply by r, shift things over, and combine like this. I'm going to show you another way to prove the geometric series because it's so important. And this proof is going to highlight one of the most important ideas in game theory. So again, because you guys are all older and taking a graduate level class, we don't do the fun toys anymore. Okay, so I'm trying to get this to turn over a little bit. All right, so we're not going to, you have to walk like this a little bit, and there you go. Okay, so what I would normally do is you'd be shooting. I would have 2 people, either from the class or Larry Bird and Magic Johnson, because I'm old. And I would assume the first person makes a basket with probability P, the second person makes a basket with probability Q. The people never tire, they never get bored. They're willing to spend the rest of their life shooting baskets until one person makes a hoop. All right, so A, probability of a basket is P, B has probability Q, and I'm going to let R be 1 minus P times 1 minus Q, which will be very useful in a moment. And now what we can do is X equals the probability A wins, A shoots first. All right, so we want to calculate what is the probability that A wins given that A shoots first. All right, so how can we calculate X? Well, you could win on your first shot, which happens with probability P. How could A win on their second shot?
If B misses their first shot and A makes their second shot.
Or you got to do a little bit more than just B misses. RP. A has to miss first, then B misses. Or A could win on its third shot, so they both miss twice. And you see, this is just X is equal to P times 1 plus R squared plus dot, dot, dot. There's another way to calculate this. So A could win on their first shot. Now imagine A misses and B misses. From this point onward, what is the probability that A wins? It's the same as the probability from the beginning. This is because it's a memoryless process. There are a lot of things that are not memoryless. If you're playing a game of chess, is chess memoryless? As long as you come to the same configuration, does it matter how you got there? There are some versions of chess where if you have a threefold repetition of board positioning, it matters. So you've got to be a little bit careful about something like that. Okay? For the most part, though, I think we can assume chess is something like all that really matters is what's the position of the board. It doesn't really matter how we got there. And so now that we have this, we can solve. We get x times 1 minus r equals p. So x equals p over 1 minus r is p 1 plus r squared. And there's the geometric series formula. And it illustrates a great idea of this memoryless process. Now, what are the restrictions on r? For this part, yes?
It has to be positive.
R has to be positive. It can be a little bit less than positive.
Not.
So 0 less than equal to r. Do I need anything else?
1.
Can r equal 1? No. Strictly less than 1. If r equals 1, that means that p is 0, q is 0, and nobody ever makes a basket. All right? We're not going to analyze that case. Okay? I'll leave that as an exercise. If r equals 0, what does that mean? If r equals 0, either p or q has to be 0, and you can see that this will work as well.
Has to be 1.
I'm sorry, either p or q has to be 1. Thank you. So those extreme cases are not so bad. So unfortunately, this argument only works if r is between 0 and 1. We want all values of r less than 1 in absolute value. As a nice exercise, you can actually deduce what happens if r is negative from this. So if you want a nice exercise, is prove the geometric series formula when r is negative just from knowing this. To get complex values is a little bit harder. Okay? Now it's already absurd to talk about, Larry Bird makes a basket with probability I over 2. Or even just negative a half. That's already absurd. But you can use analytic continuation. And so if you know it for r between 0 and 1, r between negative 1 and 1, you can get the complex case as well. All right, why do I care about this? This gives me a way to tell when a series converges. This is the prototypical example of a series that converges. Now that we have that, we can come back over here and look at, when does this sequence converge? So, there's all these different types of convergence you can talk about. I'm not going to get into too much detail. We'll say rho is radius of convergence if the series, the sum of an x to the n converges for all absolute value of x less than rho, and rho is the largest possible. So it seems clear that the larger I take rho, the more difficult it's going to be for the series to converge, because the terms x to the n are going to get larger and larger and larger. The smaller I take rho, the more I restrict the x's, the smaller the x to the n's are going to be, the easier things will be to converge. So there's lots of different tests you can do. One of the most useful is the ratio test. So you can take rho, or actually 1 over rho, to equal the lim sup of an to the 1 over n. And I'm going to just sketch why this gives you convergence. And the idea is the following. If you look at an x to the n in absolute value, well, if 1 over rho is the lim sup of an to the 1 over n, then that means eventually when n is really, really large, 1 over rho to the n, is that going to be a little bit larger or a little bit smaller than this? So let's think. So when n is really, really large, we're going to have an versus 1 over rho to the n. Which do you think is going to be larger, the an or the 1 over rho to the n? When n is very large, which way do you think it's going to go? So what does lim sup mean? All right, how many of you remember lim sup from analysis? All right, what does lim sup mean?
The supremum is listed as n tensor.
Okay, so do you think these will be larger or smaller than that eventually? If I make this a little bit larger, so if I do an versus 1 over rho minus epsilon to the n, I've made this a little bit larger. Or I could make this a little bit smaller. So the lim sup is the smallest number that works, right? So if I took a number that was a little bit larger, would it still work? Or would it be too large? So I'm looking at an to the 1 over n. And eventually, let's say it's monotonically going towards 1 over rho. And so here is 1 over rho. It's got to be somehow converging to it. And this is going to be the largest number that works. If I take a number that's a little bit larger, 1 over rho minus epsilon, eventually I'm going to be much lower than that. If I take 1 over rho plus epsilon, eventually I will be larger than that. So eventually an should be less than equal to 1 over rho minus epsilon. And this should hold for any epsilon. Because if it didn't hold, then 1 over rho is not the lim sup. I could have taken something a little bit larger. So when I look at this, this would be less than rho minus epsilon. And xn is going to be less than rho. So this would be to the nth power. This would be rho minus, say, epsilon tilde to the n in absolute value. And now all I have to do is, x is less than rho, so assume x is less than rho minus epsilon tilde. Choose epsilon less than epsilon tilde, so that the denominator is larger than the numerator. I'm a little bit away from rho over here. Just choose this number to be closer to rho. And now I have a series that's dominated by a geometric series. So since my series is dominated by a geometric series, it has to converge. And now we just win by the comparison test. So this is what's going on with the ratio test. This is why the ratio test works. The ratio test is just an intelligent way of comparing to the right geometric series. And we figure out which geometric series to look at by calculating the radius of convergence. Okay? So you can now tell whether or not a series converges or diverges by calculating the lim sup of a into the 1 over n. There's other tests you can do, but this is a particularly nice one. And now once we have something like this, we have series. So we have sums. The next question is, once we have a sum, we want to know what else can we do to that sum. So what are some things you might want to do to a sum? Now, I give you a sum, what would you like to do to it? Wish list. Differentiate it, right? What's the derivative of a sum? The sum of the derivatives. How many of you have seen a rigorous proof of when you can interchange differentiation and summation? Okay, this is one of the things I want to talk about because this will be useful in a lot of things. And in fact, in the Benford's Law papers, which some of you have worked on this summer, you were interchanging sums and derivatives. And so I want you to now see why this can be justified. If you know complex analysis, it's actually much easier because you're only looking at nice functions where things work well. Real analysis is much harder. But the main idea is if we have a function that converges, inside the radius of convergence, I have nice absolute convergence. And if I differentiate, things are fine. So assume inside radius of convergence. So I have the sum an x to the n, and this gives me some rho, 1 over rho is lim sup of an to the 1 over n. All right, if I take the derivative, morally, what should I get? Physics hats are required for this course. What do I get if I take the derivative? So what should this derivative be? So you're nodding your head, Andrew, so I'm putting you on the spot. Right. So the fact that I have x to the n minus 1 shifts all my n indices by 1. That doesn't really matter. So now I would get, 1 over rho tilde would be the lim sup of n an to the 1 over n. And again, I don't care about n versus n minus 1. Doesn't matter. Well, if I look at this, I have n to the 1 over n. What is n to the 1 over n? What does n to the 1 over n go to? So how would I figure out what n to the 1 over n goes to? So imagine n equals 10. I'm talking about the 10th root of 10. Well, the 10th root of 10 is clearly going to be less than the 8th root of 10, right? At the 8th root of 10, well, the square root of 10 is about a little over 3. Square root of 3 is about 1.7. Then I need the square root of 1.7. What do you think the nth root of the 1 over nth root of n is going to go to? 1. And so this gives me a chance to illustrate one of my favorite proof techniques. You should have a Pavlovian reaction. And enough of you have taken a class with me so that as soon as I say Pavlovian reaction, you should know what to say. Yes? Take the logs, right? Whenever you have a product, you should instinctively salivate. Well, if you don't have to, that's up to you. And you should just take logarithms, okay? Where's the product here? I have this n to the 1 over n. So if I let, L equal n to the 1 over n, the log of L is 1 over n, log of n is the log of n over n. Can I calculate this limit? Yeah. How can I calculate this limit? So how would I calculate the limit of log of n over n? What would you use? You've got to answer because it's been a while since some of you have taken analysis and I want to know what you remember and what you don't remember. How would you evaluate the log of n over n as n goes to infinity? Yes?
It says less than square root
Well, how do you know log of n is less than square root of n?
How rigorous of an answer do you want? Like it grows slower.
Well, okay, so prove it grows slower. How would you do that? So one is L'Hopital. So that's one way to do it. If you want another way, we don't have that much time left, is I could let n equal e to the y. And then the log of n over n is the same as y over e to the y. And now knowing the Taylor series of e to the y, it's great if I just keep one term in the denominator. This would be less than or equal to y divided by y squared over 2 factorial. And that will clearly go to 0. So if you don't remember L'Hopital, here's one way to get it just using very elementary arguments. Because again, I don't really care about the rate of convergence. This now gives me that the log of n over n goes to 0. And therefore, n to the 1 over n goes to 1. Therefore, these two series have the same radius of convergence. Okay? And that's a wonderful fact. That if you have a series that converges inside the radius of convergence, you can differentiate term by term. So if I give this the name f of x, I could call this Bob of x, but what is a much better name for the second one over here? I'm trying to figure out exactly how to stand so the camera goes. There we go. What should I name this function over here? F prime, right? That, this is what you want to call it. That's a theorem, right? Have we proved that this is f prime? Have we proved that this is the derivative of f? Yes or no? Why haven't we proved it's the derivative of f? We calculated, we showed it converges.
We put the sum of the derivatives is the derivative of the sum. Oh, no, you can't just do that. So what do we have?
Well, I mean, I've shown that this sum converges, right? So why the hell don't I know it's f prime of x? The sum converges. Converges nicely, yes?
We don't know what it converges to.
We don't know what it converges to. Isn't that annoying? Right? You know that it exists. Every fiber in your being should be saying it equals f prime of x. But we haven't proven that. So as a problem to ponder as you continue reading the Fourier analysis chapter, prove that f prime of x actually equals f of x. Go through this. The way I like to do this is I like to do what's called a 3 epsilon proof. But this is a good thing for you to just practice your analysis and see if you're able to do this by next class. Shoot me an email if you're having some difficulty. Happy to provide some hints. It's not entirely trivial to do something like this. This is a problem where it's really good to just bang your head for a while and just get a sense of how you try to calculate this. What do you think might be useful for a problem like this? I want to prove that this equals f prime of x. What might be a useful starting point? We've already used it once today. Yes? The definition of the derivative. Just because this lecture was prepared while my wife was driving us back from New Jersey does not mean this was not a well thought out lecture. The definition of the derivative, right? How do we know what f prime is? Well, we know the definition. The limit as h goes to 0, f of x plus h minus f of x over h. And you have something like this. And then you want to try to figure out how to do this. And the key idea that you want to use is the definition of the derivative, and you want to somehow also use the fact that any finite sum is easy to work with. All right. So what I'm going to do now is, this ends the lecture proper. We have another 20 seconds. What I want to do now is, this is the beginning of the semester. I want you to really think about this and send me some feedback, either directly with your email account or anonymously. Do you like lectures like this? I'm trying to dwell on points that you probably have not seen in previous classes and really emphasize some of the subtle issues while giving you time to go home and play with this. I don't want to go through definitions. Trust me, it's much easier for me to go through definitions. It's much easier for me to prepare the lectures. but I don't think it's as useful for you. I want to try to highlight the big ideas and the big guiding principles behind all this analysis. And so, let me know how this is going. We're going to continue talking about this, and we'll now actually get to differentiating the geometric series next class. All right, so I'm going to try to turn this off so it doesn't seem